Hello, everyone, and welcome back to Neutralizing COVID, the monoclonal antibody story, the podcast where we unpack the science, strategy, and real world impact of monoclonal antibodies in the fight against COVID 19. I'm your host, Dr. Shikha Agrawal. In this series, we explore the science behind monoclonal antibodies and their evolving role in the COVID 19 response. Today's episode unpacks how genomic surveillance influences which treatments stay and which get shelved. This is how variant surveillance informs monoclonal antibody use in context of the genomic space. Back with us is our nanomedicine expert, Dr. Aiswarya Chaudhuri, ready to navigate another chapter of antibody science and innovation. Welcome and thank you for being here.
Thanks again for the opportunity, Dr. Shikha. Thrilled to be back. I'm excited to talk about this. It's a complex but essential part of managing the pandemic.
Let's dig into the details. What exactly is variant surveillance and how does it work in context of SARS-CoV-2?
Variant surveillance refers to the continuous monitoring of the changes in the viral genome. For SARS-CoV-2, this typically involves sequencing the virus from the infected individuals around the world and identifying the mutation, especially in the spike protein, which is the main target of the monoclonal antibodies. This data helps scientists track how the virus is evolving, which variants are emerging, how rapidly they are spreading, and whether those mutations might affect the virus's behavior or resistance to treatments.
Very insightful. So, where does that leave us in terms of monoclonal antibodies? How do these mutations impact effectiveness?
Monoclonal antibodies are designed to bind to specific regions of the spike protein. If the virus mutates in those regions, specifically in the receptor binding domain, it can reduce or even eliminate the ability of an antibody to neutralize the virus. This means that some variants may evade the existing monoclonal antibodies, rendering certain therapies less effective or even obsolete. That's why continuous surveillance is so critical. It informs the decisions about which monoclonal antibodies are still useful and which may need to be updated or withdrawn.
Now, how quickly can we respond when a new variant shows resistance to an existing monoclonal antibody?
That depends on a few factors. Surveillance networks often identify key mutations within weeks of the emergence, but adjusting treatment guidelines, conducting lab-based neutralization assays, and rolling out updated antibodies can take longer, sometimes several months. So, regulatory agencies and pharmaceutical developers have developed faster pathways for evaluating the modified monoclonal antibodies, but it's still a race against time. The virus mutates continuously, so staying ahead requires a coordinated and agile system.
Are there examples where surveillance data has directly changed the use of a specific monoclonal antibody?
Yes, several monoclonal antibodies that were once widely used were later deauthorized or restricted due to emerging resistance. For example, some early antibodies lost effectiveness as Omicron and its subvariants became dominant. Once data showed a significant drop in neutralization ability, health authorities adjusted the recommendations accordingly. That's the genomic arm race. As the virus adapts, we must adjust our therapeutic tools in response.
I can't help but wonder now if this means that future monoclonal antibodies will need to be more adaptable or broad in their targeting.
Exactly. There's a growing interest in broadly neutralizing antibodies, monoclonal antibodies that target conserved regions of the spike protein that are less likely to mutate. Some newer candidates are designed with combination of antibodies known as antibody cocktails to reduce the chance of complete escape. Another approach involves engineering antibodies to retain binding across various or multiple variants. It's a challenging goal, but a necessary one in the face of ongoing viral evolution.
Let's continue by exploring variant surveillance. How globally coordinated is variant surveillance and what role does that coordination play in monoclonal antibody deployment?
Global coordination is essential. Institutions and governments contribute sequencing data to international platforms, creating a real-time picture of viral evolution. The more diverse the sequencing data, the better we can anticipate resistance patterns and adapt monoclonal antibody strategies on a global scale. That said, inequities in sequencing capacity can limit the surveillance in some regions, which makes the overall system less robust. Strengthening global sequencing networks is critical to ensure that antibody-based interventions remains effective everywhere.
Looking ahead, how can we strengthen the link between genomic surveillance and antibody development?
We need tight integration between the surveillance teams, virologists, and therapeutic developers. That includes real-time data sharing, predictive modeling of mutation impact, and faster platform for antibody redesign and testing. Investing in flexible monoclonal antibody development pipelines, ones that can rapidly respond to new variant data, will be key for both COVID-19 and future emerging threats.
Dr. Aishwarya, this has been a truly insightful conversation. Variant surveillance may not be visible to most people, but it's clearly one of the pillars of staying ahead in this pandemic.
Absolutely. It's the quiet engine behind many of the decisions made in treatment and prevention. And thanks for having me.
That's it for this episode of Neutralizing COVID, the monoclonal antibody story. As we have heard, monoclonal antibodies are only as good as the data that guides their use. And in a world where viruses evolve, vigilance is everything. A huge thanks to our listeners. Don't forget to follow us and share this episode if you found it valuable. Until next time, take care and keep exploring science.